Thank you for the nice introduction, and thank you so much for inviting me to this very interesting and nice event. I don't work on oncology data. I work on natural images predominantly so far. And when I was younger, I would present now a talk with my new fantastic model, and I would show you what it all can do. But nowadays, I can no longer build foundation models myself, so instead, I will talk today about models by somebody else and tell you what they cannot do. Since we're doing artificial intelligence, I want to start off with a short history of intelligence. And at some moment in time, our world was occupied by animals like sponges, worms, and jellyfish. And this was sort of like enough diversity for the world to prosper. And then all of a sudden, the Cambrian explosion happened. And the precise reasons are unclear, but likely it became much lighter on our planet, and eyes started to develop, so sensory perception skills. And because of that, suddenly animal species acquired all kinds of attributes like claws, tentacles, and armor, and life became a matter of eating or being eaten. So diversity prospered, and all kinds of animal species developed, and also intelligence started to develop. We make a jump. This is a blueprint of a macaque brain, the animal that is closest to ourselves. And famous cognitive scientist Van Essen sort of like made a blueprint of what the brain of this macaque does and what are the different functional components in this brain, to find that about 50% of the macaque brain, and there's also of the human brain, is devoted to vision. So although we live in the times of large language models, I would like to make a case that vision is far more important for our intelligence. So the human invention of written language is of a much more recent origin. So it likely started in Mesopotamia, so the area now known as Iraq, and it slowly evaded all of the world, all kinds of civilizations, had small modifications and so on, but it's a relatively new invention. ChatGPT is even more recent, from November 22, and of course it has amazing abilities, but today I want to talk about multimodal models, and for me multimodal then means a combination of vision and language. And instead of highlighting ChatGPT, I would like to highlight another great model by OpenAI, that is their CLIP model. They presented this at ICML in 2021. And basically, the recipe of building this CLIP model is super simple. So essentially what CLIP is doing, you collect millions of images from the internet. You just scrape them from the web, and because they are embedded in a web page, they often also have an alt attribute in their HTML tags, and this alt text is then a description that you can use as sort of like a ground truth of what is depicted in the image. You cannot use this as is, so you have to do some filtering and some curation to assure that indeed the text corresponds to the image. But if you have then collected a large enough bunch, you can sort of like run this through your favorite encoder. So the images go to a vision encoder, the text goes to a text encoder, you get an embedding, a vector, and then you, by means of an algorithm called contrastive learning, you force the images and the text that belong together to have the embedding that becomes closer in this high-dimensional space, and a sentence that is not related to the picture of interest should be far away in the embedding. Now, if you do this at scale, you get amazing zero-shot abilities. And this model, although maybe less well known to the general public, is actually very, very powerful as well, and has been used a lot in my field. So here's sort of like a follow-up work from Google DeepMind. It's called Flamingo, and here they show this property of in-context learning. So once you have pre-trained such a multimodal model, you can learn it to do a new task based on a very few set of examples. So if you look at the first row, you ask, you give it a short description, together a prompt together with an image. So you say this is a chinchilla, they are mainly found in Chile. Then the other one, this is a Shiba, they are very popular in Japan. And then you give it an image of a flamingo and you say this is, and the system will sort of like fill in the words and will tell you, well, it's a flamingo, they are found in the Caribbean and South America. Okay, that's nice. But now look at the third row. So here you give it an image and you say there is overlay text in the image, so the output should be underground. And in the next image you say the output should be Congress. You give it a new image with a title of a municipality somewhere, and it will output, indeed, this is Sulome. So this is very interesting. So all of a sudden it has learned the ability to do OCR, basically from giving a few examples. The last row is even more spectacular, I would say, because there is a simple mathematical equation depicted in the pixels, and based on a few examples, you can then solve this mathematical quiz. Amazing. Here's another example. This model is called Blip2. It's from June 2023. And this system is able to do dialogue, so you can ask it questions. So given this weird picture, and you say to the system, is this photo unusual? And it will answer like, yes, it's a house that looks like it's upside down. Okay, interesting. And then how could someone get out of the house? And then it answers, it has a slide on the side of the house. I only noticed this slide myself when I was reading the answers. I didn't actually realize there was a slide on the house. So it's quite amazing. Also the one on the right, so what is shown in the photo, a man and a chicken. Well, it's factually not correct because it's a rooster, and maybe also not so spectacular. An image that classifier can do this too. But then the next question, what does the man feel and why? And then the system switches automatically to saying, well, he's scared of the chicken because it's flying at him. So this level of at least perceived understanding is quite fascinating. All right, so what is left to do for a professor without compute? Well, let's see. So I'm going to talk about multimodal foundation models and what they cannot perceive. I have included 4 topics for today. I'm not sure whether I get to all of them. I want to cover scarcity, space, time, and human values. So let's start with scarcity. And this is work that is forthcoming at CFPR next June, together with Yunhua Zhang and Hazel Doughty. And here we got inspired by natural language processing, because many of the innovation these days also in computer vision come from NLP, because they were doing these big models first. So they had many of the insights as first, right? So, and one problem in NLP is low resource natural language processing. So they have been looking into, of course, many models work well for English, for Chinese, maybe for Spanish. There are models for Arabic, but maybe for other languages like Dutch, it is much more rare. So there are many low resource natural languages in the world, and actually you want to work on these also and develop models and see what you can do. So we figured, oh, that's very nice, because we are not aware of any low resource vision equivalent for this problem. So we defined the task of low resource vision. So to give you an example, basically many of the vision problems in the literature work on high resource data that is scraped from the internet. So usually it's easy to acquire big amounts of data. The data is typically coarse-grained, so the categories in these data sets are nicely separable because they do not overlap too much, and the domain is quite general. Now, low resource is the opposite of this domain, so often very limited data, even on the internet. Categories are typically very fine-grained, and differences are very nuanced, and the visuals of the domain are very specialized, so not something that you will easily find on the internet as well. Now, to give you some examples, we collected data, and because it's low resource, you don't need to collect a lot, and we defined also tasks. So one of the tasks that we defined and for which we collected data is circuit diagram classification. So given the circuit diagram on the left, the goal of the task would be to predict that this is a diagram of an audio amplifier. Another one is historical map retrieval. So there are historical maps, of course, but not too many are digitized or are available. And we define the task of giving a historic map, for example, of the city of Amsterdam. Can you find also the same city in a database of modern satellite imageries? And last but not least, we defined a task called mechanical drawing retrieval, where we have a three-dimensional view of a certain object together with its 3D rendered image. And the goal is to retrieve the one or the other. Here are some statistics. So for each of these three tasks, we collected data. So typically in the order of hundreds of images for training and validation, and also for testing. And the first thing we did is we ran existing vision foundation models on these tasks to see what can modern vision foundation models do. So we tested SAM, Blip, Clip, and ImageBind. ImageBind is a model from CVPR 2023. And that last one seemed to be the best one across the board, but notice that the accuracy numbers are really in the low range. So these tasks are really hard to do with these modern foundation models. So that's good, because then we could make a case that indeed this problem is different, and existing models have limited ability to address them. So our goal was then but what can we do to make them suitable for this problem? Of course, you can try to collect more data and train a model from scratch, but instead what we try to do is make a small adaptations to these existing pipelines to make them suitable for low resource challenges. So we have three challenges. So we have data scarcity, we have the fine-grained nature of low resource, and the specialized domain. And for each of these three challenges, we built very simple adapters, tricks you may call it, to make existing models better. I will go briefly over these three baselines. So the first one is that we use stable diffusion to generate data. And you can do that in two ways. One is you create more of the same of the data for which you have a label. So that is what everybody would do. So you have a certain map of a city, and you create a similarly looking map of that same city. But since you don't have a lot of data to start with, that will not grow your data set fast enough. So what we also do is we generate, by playing a little bit with the parameters of stable diffusion, you can sort of like make things that look somewhat similar to things that look very dissimilar. And we wanted things that looked very dissimilar. And if you do that based on the same input image, those two dissimilar images will look alike. And then you have lost the label, but you still have valuable training samples for your contrastive learning. So here are some examples. So in the first column, there are examples of an FM transmitter, and these still look the same after stable diffusion. On the other ones, we have sort of like increased the knob to make them really different from the input image. And although you can no longer call this an FM transmitter, the images in the same column look very similar. So they are valuable examples to learn from, although they have no label anymore. So this is trick number one. Trick number two is that we often work in low resource data. The data is often very fine-grained. So fine-grained details in the image are important. We can do this by making the tokens smaller and retraining, but that is too much work. So instead what we do, we create a new tokenization layer that basically splits an existing token into 4 areas, and then we have new parameters that we can optimize to sort of like learn what part of the token was beneficial. And because this is already a limited number of parameters and we have a limited number of data, we can still learn a useful signal from it. So that's trick number 2. Trick number 3 is to look into the attention mechanism of the transformer. And instead of learning global attention only, we also look at where is the attention in the image, and we make a crop around this attention value, and we combine these tokens with the multi-head self-attention. So we get a richer description. Now, then we present a lot of tables in the paper to show, look, each of these components add a little bit, and when you combine them, they are actually very effective, and that one I will highlight. So here you see, for the task of historical map retrieval, we added these 3 simple tricks to clip, to blip, to image bind, and to SAM, and then in the first row you see out of the box zero-shot transfer, and when you add these 3 simple tricks, you can actually increase performance quite a bit. So I think that's quite interesting. And although we improved the zero-shot transfer of these models, there's still a long way to go because many numbers are still very, very low. Here are some results of what the models can do. So we can classify a circuit diagram as a dice or a power supply, and find the map of Winnipeg also in modern times, and so on, especially if the problem is distinct. But there are still also many hard samples. So this is where we fail. For example, the Innsbruck map was very hard because the style of the map was very different from the few that we had in our data set. So still a lot to do. This was problem number 1, scarcity. Now we go into space. So what can models do with space? And this is also a forthcoming CFPR paper together with Michael Dorkenwald, Nimrod Barazani, and Yuki Asano. And of course, there are many specialized computer vision models that can localize an object in image data. So these results this is a well-understood problem, and there are very dedicated approaches that can do this detection and segmentation really, really, really well. But these are specialists, so they can only specialize on these tasks. We are interested in what can these vision language models, these clip-like models that are trained on images and sentences, can they also localize objects? So we did a bunch of tests. So here's a prompt, and the question is, we ask several of these vision language models, can you provide a bounding box around the person? So there are 2 clearly distinctive objects in this image, so you would say, well, this is maybe easy, but let's see what these models can do off the shelf. So we tried Open Flamingo, Fromage, and Blip 2, And basically, none of them can sort of like interact with these types of questions. They just try to fill in the next word, right? That's what they trained at, and that's what they do here. We also tried GPT-4V, and we don't know the internals of this model because it's closed. So maybe it is trained on box data, we don't know. But at least it has a notion of spatial understanding, because it tries to fit a box into the picture. Not quite precise, but at least it's doing something. Here are a few more examples. So the one with the dog is rather easy, I would say, because there's only one big object in the center of the image. So all you have to do is put a box in the middle. The other one, the last one, is more involved because there are multiple objects and you really need to know what is where. Now, as expected, OpenFlamingo, Fromage, and Blip2 cannot do much. GPT-4 Vision I consider correct. And for the other one, also GPT-4 Vision has the head, but not quite well aligned. We also tried to vary the prompt a bit to maybe make sure that maybe they have another understanding of pixel space. So we tried with sort of like an index on multiple patches in the image, and then that became the prompt. So can you specify what squares belong to the object? And also here, none of them was able to make sense of this task. We also tried sort of like chessboard pattern. So maybe these models have been trained on chess games and then have sort of like a spatial understanding of what's going on. But also that didn't really fly well. So no matter the model. Another task on spatial reasoning, where we ask what is to the left of the pizza or above the pizza or to the right. And results are mixed, but none of them is consistent in always doing it correct. Okay, that's nice. We have something, we have found a limitation of existing models. Now is the question, can we also fix it? So that is why we propose a PIN, our positional learnable prompt that you can add to existing vision language models, together with synthetic unlabeled images, to sort of like inject this ability of localization into existing models. Now, how does that work? We take a vanilla Flamingo model, in this case OpenFlamingo. So this is a vision language model. We keep almost all parameters frozen. We just make one small insert, and that is what we do over here. So after the output of the vision encoder, we add our PIN, our positional insert. And it starts from a one-dimensional sinusoidal embedding with only 64 dimensions. And from there, a two-layer MLP, a multi-layer perceptron, is applied, each consisting of a fully connected layer and a layer norm and then a sweet glue activation. So then another fully connected layer to make it 2024 dimensions, so that it resembles the output of the original vision encoder. And that we put into the fusion network. And so for the people who know Flamingo, that is a perceiver type mechanism. And then it goes into the large language model. Now we need the ability to do localization. So that works as follows. So in the image is a dog located at. And then we want the system to output box coordinates. Now the question is, how do we feed the system with these box coordinates? We don't want to label images and give box annotated examples, because that's easy. We already know that works. So instead, we want to sort of like optimize this loss not with provided bounding boxes, but with synthetic data. And again, we rely on stable diffusion. And with stable diffusion, you can generate really nice images that you can, of objects. And we take as source, we take the Elvis dataset. This is a dataset of objects that are especially for the long tail, so also more rare objects. And we paste these objects into a standard dataset of background images, so scene images. So you see some examples depicted. So for example, we have an image of a forest and then a big goose pasted in there. And because the quality of this stable diffusion is so good, although these pictures do not look realistic themselves, they are good enough for learning. Now, let's see how this pipeline works. So synthetic data generation works as follows. We have a certain background image. We generate an object, say a monkey, and then we paste the monkey somewhere in this image. And because we know the size of the monkey and we know where we paste it, we also have its coordinates and we also have its box coordinates. So we have the bounding box that belongs together with the monkey. And then we have all our ingredients in place. So we have an annotated data set that we generated ourselves, together with this frozen vanilla flamingo model, plus our pin module, so to say. We train the parameters of this pin module, and then we are able to output at inference time. In the image is a banana located at, and it will give you the box around the object of interest. So, very lightweight procedure without the need to label any images yourself. It's all reliant on external models. So here are some examples. So you have to ask the model what object you're interested in, so it cannot label the object category, but if you tell it where is the person, it will give you the bounding box around the person, or around the owl, or the apple, or what have we. Not perfect, but I think the point that we want to make with this work is that although these models do not have this capability out of the box, it is feasible to inject new abilities in these models. I think that is a very interesting finding. So not competitive with mask RCNN or whatever, right? But it's an ability that can be injected into a pre-trained model without pre-training from scratch. The third one is time, and this is about video language models. It's from CFPR last year. It was with Piyush, a student who is now in Oxford, Makarant Tapasvi from IIT Hyderabad in India. And here the problem is, so image language models are great, but the same ability for video language models is even more interesting because videos are multiple frames in a sequence, and being able to sort of like understand what is happening at every single instance of such a video gives a very rich description and a very rich understanding. So many people have done this type of approach. What does this picture show? It will say dog running. And for video, you can do the same. So what does this video show? And then it will output a kid eating an ice cream. Now, here we ask the questions, do these existing video language models really understand time? So do they really have an awareness of temporal understanding? Or maybe they are just image classification models on steroids, and they don't need to understand time because they can just say, based on a single image, they can already say the kid is eating ice cream, right? As the most characteristic frame from this video. So Piyush defined a test of time where he asked very simple before and after questions to these models. So here's a question. The baby eats ice cream before walking downhill, true or false? So very simple question that requires understanding the entire sequence of the video, and really the system now has to realize that eating the ice cream happens at the end and not at the beginning. So, how to make this operational? So we created a synthetic benchmark where we sort of like programmed the dataset, and the dataset consisted of very simple colored shapes that have before and after relationships. So for example, a red circle appears before a yellow circle. That's then the correct sentence. And the wrong sentence for this video would be a yellow circle appears before a red circle. So the task then for the video language model is to say, is this sentence correct given this video, or is the other one correct? Now, to prevent that we were making it so an exotic data set that all methods would be upset simply because they have never seen those pixels, we also created a control task where there is no temporal relationship whatsoever, and we just ask, does this video contain a red circle or does it not contain a red circle? We took 7 off-the-shelf video language models, and we tested this simple test of time test. So we asked each of these models, can you do these simple tests? And it turns out that all of them were as good as chance or worse. Well, most of them could solve the control task. So the conclusion is that all these video language models have no understanding of time, at least not of before and after relationships. Also here we are interested, can we update these existing models after they are pre-trained with temporal awareness? Of course you could do this by pre-training them again with the objective of interest, but that's a huge computational effort. So image language is already computationally demanding at scale, but video language you don't even want to do. Well, turns out that many of the existing data sets in this domain for video captioning, you can easily repurpose by adding extra before and after relationships to their data. Because very often it's a long video sequence and one part has a sentence and another part also has a sentence. So then you can just connect them together as before and after relationships. So that creates a new type of data set that you can then feed into your model to fine-tune on before and after relationships. So that you explicitly force the model to fine-tune on before and after relationships. Now this is more of the same. This is just the encoding, not so interesting. And then you can go back to standard contrastive learning, because you will have a video and the before and after sentence, so to say. So you have the usual positive and negative examples, but because you have you can reverse the before and after, so you can make really hard samples, so you can do hard negative mining much better in this setting. And flipping them around also gives you extra positives. So with a very simple trick, you make the data set much richer for the temporal awareness task you are interested in. Again, we did a bunch of experiments on data sets that matter for these problems. I don't think it's important to know all the details. Here you see a plot, and I think this is of interest. So on the y-axis, you see the accuracy in temporal ordering, so the synthetic task we defined, so higher is better. And on the x-axis, you see the regular performance for each of these data sets and the benchmark for which they are developed. And here, the more to the right, the better. So the sweet spot is in the top right corner. Now, red is the baseline, and blue is after our post-pre-training procedure, right? So after our fine-tuning on this spatial or this temporal awareness. Now, what we see is that indeed the temporal order now is much better captured, and most often also the accuracy for the original task for which the benchmark was designed also improves. I'm almost done. Last but not least, human values. We don't have a CFPR paper for this yet. This is a work in progress. We just started. And I think this is a very fascinating topic because these AI models are now becoming so powerful and we are bringing them into society, but we don't really know what we're doing. And this has some consequences. So maybe you have seen this photo before. This is the moment that an Uber car, who was in self-driving mode, crashed into a pedestrian who was crossing the street at night somewhere in Phoenix. Unfortunately, the person died during this incident. So the car simply didn't recognize that an event of interest happened. So very robust model, but not robust enough to guarantee safety. This photo appeared on X, and it had an effect on the New York Stock Exchange, because people believed that the Capitol, or not the Capitol, what's it called? The building where all the security is, the Pentagon, was on fire. And an official statement had to be issued by the American government that it was a deep fake. So Stable Diffusion is a great tool to create data sets for injecting spatial awareness into video language models, image caption models. But you can also do these kind of things. Here's another example. Other side of the medal. These are results of Google Gemini, where based on the query, can you show me some images of diverse US senators from the 1800s, it will create, it will hallucinate a reality that is also not true. Maybe we wish this was true, but this certainly was not the case of a representative sample of senators in 1800. So how to do this well? We don't know yet. And here's another one. We're putting all kinds of cameras in the street. So here's a picture from Amsterdam and one from Beijing. But who has control over these cameras, and what type of software do we put on these cameras? And what happens with all the intelligence that they record? And who makes this actionable, and how do we guarantee privacy and legal questions? I don't have the answer yet, but we have found a bunch of researchers all over the University of Amsterdam from 7 different faculties to study this in a multidisciplinary setting. So how can we make these foundation models human-aligned, so to say, so that they comply with human values, so ethical values, legal values, but also align them with human cognition. And we also defined several interesting use cases. For example, in surgery, surgeons are trained on video recordings of surgery. How can you sort of like give them access to these videos and do that in an ethical and legal way, if at all, right? These models can be very supportive in sort of like assisting the surgeon, to telling them, oh, you have missed something, or are you sure you don't want to operate in this area over here? So very fascinating questions where AI can make a difference, but making it operational is really hard. Another one is where we work with Marie Lindegaard. She's a cultural anthropologist, and she studies bystander effects in aggressive situations. So, for example, she has found that these bystander effects are a myth because she has analyzed lots of video data, and very often when there is aggression in the street, people do respond and interfere. So she's working a lot with police camera footage And she would be very interested to also, and she does manually. So she sifts through camera images manually, but would like to use AI to sort of like make her research scale up and make it much more interesting, because more findings can be found. But yeah, how to do that? Because it's public safety data, cannot be shared, cannot be, very complicated questions. So we would like to study this, and I hope to report back on these findings in a year or maybe longer. That's it for me for now. I think my main conclusion is that multimodal foundation models are amazing. They are super powerful. They do have some perceptual difficulty with tasks like scarcity, space, time, and human values. They can be updated with small capacity adapters and also with synthetic data to fine-tune them into new directions, or to instill behavior into these models that you want. And by doing so, the bonus is that this is sustainable and also responsible, because you don't need to retrain from scratch. And with that, I would like to close. Thank you.